All right, diving in. Quantum computing.
Yeah.
It's really changing fast.
It is. It's a wild ride.
Whether you're, just figuring out what a qubit is.
Right.
Or you've been, knee-deep in this stuff for a while.
Yeah.
It's amazing to see.
Definitely.
We got a ton of stuff to talk about today.
Yeah, real mix.
Some brand new announcements.
Some deep dives on the research.
Yeah, papers and all kinds of things.
The latest and greatest.
Really, the goal is to kind of make sense of it all.
Absolutely.
For everyone.
Whether you're just starting or you're already an expert.
Right, exactly.
We want to make it engaging and exciting.
So think of this as your guide to what's really happening.
A deep dive into the source material.
Yeah, what matters.
Exactly.
We're going to look at some new hardware.
Yeah.
Really interesting new chips.
And Amazon's Ocelot.
Google's got something.
Willow, a very different approach.
Then there's the whole Microsoft thing with topological qubits.
Right, that's a completely different beast.
And we can't forget about error correction.
That's the key to unlocking the power of these machines.
Yeah, they're super sensitive.
Unbelievably so.
Any little disturbance can throw them off.
It's like trying to write on a piece of paper while on a roller coaster.
So we have to figure out how to fix that.
Absolutely. And there are some really clever ideas out there.
And then there are some actual real-world applications starting to pop up.
Yeah, we're starting to see the potential here.
Certified randomness.
Quantum key distribution from space.
Pretty wild stuff.
It's truly the beginning of a new era.
So let's dig in. What do you say?
Sounds good to me.
Let's start with the new hardware.
Right.
Amazon's Ocelot chip.
This one's a real head-turner.
Came out February 2025.
That's right.
What's the big deal with this one?
Well, they're going after the cost of error correction.
Oh, right. That's a huge obstacle.
Yeah, it's a major bottleneck right now.
Expensive.
Incredibly so.
Uses up a lot of qubits.
Exactly. And Amazon claims they can cut that cost by up to 90%.
Whoa. 90%.
It's a game changer if they can pull it off.
Yeah, how are they doing that?
It all comes down to their new architecture.
Right.
Developed at their AWS Center for Quantum Computing at Caltech.
Fancy.
Very impressive team there.
So what is it? What's this new architecture?
They're using something called cat qubits.
Cat qubits.
Yep. Named after Schrodinger's cat.
Oh, the thought experiment.
Exactly, the one where the cat's both alive and dead.
Right.
It's a bit of a playful nod. But the idea is that these cat qubits are inherently more resistant to certain types of errors.
So instead of fixing errors after they happen?
They're trying to prevent them from happening in the first place.
That's clever.
It's a really elegant approach.
So it's kind of like built-in error correction.
In a way,
and they've managed to put all this onto a single chip.
That's right. They've integrated the cat qubit technology with the other components needed for error correction.
Wow.
All on a scalable microchip.
So they're thinking about mass production.
Absolutely. They're even using manufacturing techniques from the microelectronics industry.
Interesting.
Yeah, they want to be able to churn these things out.
Make them affordable.
Exactly.
Oscar Painter, the AWS director of quantum hardware, he had a pretty strong quote about all this.
Yeah, he said, it's no longer a matter of if, but when practical, fault-tolerant quantum computers will be available.
Really putting it out there.
Yeah, he's confident.
And he thinks this Ocelot architecture could cut costs to 1/5 of current approaches.
And that could accelerate the timeline for practical quantum computers by up to 5 years.
That's a bold prediction.
It is, but it shows how much emphasis they're putting on error correction.
Yeah, it's clearly the biggest challenge right now.
It is, because quantum computers are just so sensitive.
Super sensitive.
To everything. Vibrations, temperature changes, even cosmic rays.
Right. All that stuff can cause errors.
Exactly. And that's why we need error correction.
So how does error correction work, in general?
The most common method right now uses logical qubits.
Logical qubits, okay.
It's where you encode information across multiple physical qubits.
So you're spreading the information out.
Exactly, to make it more resilient.
Like a backup system.
Sort of. If one qubit fails, the information is still safe because it's spread across multiple qubits.
Makes sense, but that takes a lot of qubits.
Yeah, it's very resource intensive.
And that's what Amazon is trying to change with Ocelot.
Exactly. They're taking a different approach.
By designing the whole system with error correction in mind from the start.
Right. They're choosing the cat qubit and the architecture specifically to minimize errors.
So they're not just trying to fix errors, they're trying to avoid them.
Exactly.
Painter even said that scaling Ocelot to a full computer could take just 1/10 of the resources compared to standard methods.
That would be incredible, a real breakthrough.
So what does this Ocelot thing actually look like?
Right now, it's a prototype.
Okay.
2 1-centimeter silicon microchips bonded together.
Tiny.
Yeah, but packed with tech.
And they've got superconducting materials in there.
Yes, those form the quantum circuit elements.
So it's like a regular chip, but superconducting.
Kinda, yeah.
How many components are in this prototype?
14 in total.
Okay, break that down.
5 cat qubits for storing data, 5 buffer circuits for stabilization, and 4 qubits for error detection.
Gotcha. So each part has a specific role.
Right, it's all carefully designed.
And those cat qubits, they rely on these high-quality oscillators made from tantalum.
That's right, and Amazon's material scientists have figured out a very specific way to process it.
Sounds complicated.
It is, but it's all part of building a better qubit.
And this is just the beginning for them, right?
Oh yeah, they're already offering access to their quantum computing resources through Amazon Bracket.
So researchers can start playing around with it.
Exactly, they want to get people using it and developing new applications.
Okay, so that's Amazon's Ocelot.
A really exciting development.
Now let's talk about Google's Willow chip.
Another big player in the quantum game.
Announced back in December 2024.
Yeah, a little earlier than Ocelot.
And this one's making waves for a different reason.
Right, it's all about error reduction through scaling.
Okay, explain that.
So as they added more qubits to their system, they saw the errors go down?
That's weird.
It is. It's kind of counterintuitive.
You'd think more qubits would mean more chances for things to go wrong.
You would, but they hit this sweet spot where adding more qubits actually made the system more stable.
How is that even possible?
It's all thanks to their really good error correction techniques.
Okay.
They're essentially using the extra qubits to help detect and correct errors in the other qubits.
So it's like a team effort?
Exactly. The qubits are working together to improve the overall reliability of the system.
That's really cool.
It is. It's a major achievement.
And they did this benchmark computation.
Yeah, random circuit sampling, or RCS.
Okay, what is that?
It's a really hard problem for classical computers to solve.
Like impossible hard.
Well, not impossible, but it would take them an absurd amount of time.
Give me an example.
Okay, Google claims that their Willow chip did this RCS calculation in under 5 minutes.
5 minutes already.
And they estimate that it would take a top-of-the-line supercomputer 10 septillion years to do the same thing.
10 septillion? That's like...
It's a mind-boggling number.
Yeah, more years than there are atoms in the universe.
Pretty much.
So this random circuit sampling, is it useful for anything?
Not directly, not yet at least. They tested Willow on grids of qubits.
Grids?
Yeah, they started with a 3x3 grid and scaled up to 7x7.
Okay.
And with each increase in size, they saw the error rate go down.
So bigger is better in this case.
Exactly, and that's what they call below threshold error correction.
Below threshold.
It means they've reached a point where adding more qubits actually makes the system more reliable.
That's a huge milestone, right?
It is, because it means they're on the path to building truly scalable quantum computers.
Computers that can actually handle real-world problems.
Exactly.
So it's not just about raw power anymore.
Right, it's about stability and reliability.
Making sure the computer doesn't just spit out a bunch of garbage.
Exactly.
And this is one of the first times we've seen this kind of error correction working in real time on a superconducting system.
Yeah, it's a big deal.
They even reported this thing called beyond break-even.
Right, where the arrays of qubits actually had longer lifetimes than the individual qubits.
So the whole is greater than the sum of its parts?
Exactly. The error correction is actually making the system more robust.
Very cool.
It is. It's a really exciting demonstration.
And Willow has 105 qubits.
With best-in-class performance on these benchmarks,
They're definitely proud of this one.
they have every right to be.
And they've improved the T1 times.
Oh, yeah, those are crucial.
T1 times, for those who don't know,
It's basically how long a qubit can hold onto its quantum information.
before it decays.
Right, like how long it can stay in its one state before it flips back to zero.
The longer, the better.
Exactly. It gives you more time to do computations.
And Willow's T1 times are approaching 100 microseconds.
A 5-fold improvement over their previous generation.
That's impressive.
It is. They're really pushing the limits here.
But it's not all about benchmarks, right?
No, they want to do something useful with this power.
They want to solve real-world problems.
Exactly.
But random circuit sampling, it doesn't have any known applications yet.
Not yet, no.
So what are they going to do?
Well, they're inviting researchers to use their open source software, Circ.
Circ. I want.
They've got educational resources, too, like a Coursera course on error correction.
So they're trying to build a community.
Yeah, they want to encourage people to develop new algorithms and applications for quantum computers.
Makes sense. They've got the hardware, now they need the software.
Exactly.
The guy from Google Quantum AI, he also thinks this stuff is going to be huge for artificial intelligence.
Oh, yeah. He's a big believer in that.
Thinks it'll speed up things like data collection, training models.
Yeah, all the computationally intensive tasks.
And he thinks it'll help us simulate quantum systems.
Which is crucial for things like drug discovery and material science.
So it's not just about building better computers.
Right. It's about using them to solve some of the world's biggest problems.
Okay, so we've got Amazon focused on cost with Ocelot.
And Google pushing the limits of scale with Willow.
Now let's talk about Microsoft and their topological qubits.
This is where things get really interesting.
Yeah, they're taking a completely different approach.
They are. It's a whole new kind of qubit.
They call it Majorana 1.
Unveiled in February 2025.
So pretty recent.
Yeah, it's still very new.
And it's based on these weird materials called topoconductors.
Right. They're special because they can host these things called Majorana zero modes, or MZMs.
MZMs, those are the topological qubits.
Exactly. They're these quasi-particles.
Quasi-particles, okay.
It means they're not really particles in the traditional sense.
Gotcha.
But they have particle-like properties.
So what makes them so special?
Well, the idea is that they're inherently more stable than regular qubits.
More stable, that's good.
Yeah, because they store information in a way that's protected from the environment.
How so?
It's all about this property called parity.
Parity, all right.
It's basically whether something is even or odd.
Okay.
And the MZMs store information in the parity of their state.
So it's like a binary code?
Kind of, but instead of 0 and 1, it's even and odd.
Interesting.
And because parity is a global property of the system...
Global. Yeah, it means it's not easily affected by local disturbances.
So like the noise we talked about earlier.
Right, things like vibrations and temperature changes.
Those are less likely to mess things up.
Exactly, because they only affect a small part of the system.
So it's like having a built-in shield?
In a way, yes.
That sounds really promising.
It does, but there's still a lot of work to be done.
Okay.
They've published their research in Nature.
The big journal?
Yeah, one of the most prestigious ones.
And they laid out a roadmap for how they plan to build a fault-tolerant prototype.
All within the next few years.
Ambitious.
Very. But they've got DARPA backing them.
DARPA, the Defense Research Agency.
That's right. They're funding this research as part of their US2QC program.
So they must believe in it.
They clearly do.
Okay, so they've got the theory, they've got the funding.
Now they just have to build it.
But they've already demonstrated some key things, right?
Yeah, they've shown how to read out the state of these topological qubits.
How do they do that? They use these digital switches and quantum dots.
Okay.
And they measure the parity using microwave signals.
So they can tell if it's even or odd.
Exactly.
Clever.
Very.
And they've got a pretty low error rate so far.
Just 1%, with plans to reduce it even further.
That's amazing.
It is, especially for such a new technology.
And the system is really stable, too.
Yeah, they only see parity flips happening about once every millisecond.
That's pretty rare.
It is, and it shows that these MZMs are pretty robust.
So it's looking good for Microsoft so far.
It is, but there's a lot of skepticism out there, too.
Really? Why?
Well, some scientists are questioning their results.
What are their concerns?
One issue is that Microsoft hasn't released all the details of their experiments.
They're being secretive.
Not necessarily, but they haven't published all the data.
And that's a problem.
It can be, because it makes it harder for other scientists to verify their claims.
So it's a trust issue.
In a way, yes.
And this isn't the first time Microsoft has run into this kind of trouble, right?
No, they had to retract a paper back in 2021.
About Majorana particles.
Exactly. So some people are worried that they might be making the same mistakes again.
That's understandable.
It is, especially when you're dealing with such cutting-edge research.
So who are these critics?
Well, there's Henry Legg from the University of St. Andrews.
Okay.
He wrote a preprint arguing that Microsoft's work is not reliable and must be revisited.
Strong words.
Yeah, he's not pulling any punches.
Was his beef?
He says that their topological gap protocol doesn't actually tell us anything about the underlying physics.
So it's like they're hiding something?
Well, not necessarily hiding, but they're not being transparent enough.
And Legg isn't the only one who's skeptical.
No, there's also Vincent Morik from Forschungszentrum Jülich.
Okay.
And Sergei Frolov from the University of Pittsburgh.
All right, so there's a whole group of them.
Yeah, and they're all pretty vocal about their concerns.
What are they saying?
Well, they're worried that Microsoft is creating hype without substance.
They think they're overselling their results?
Yeah, and Frolov even claims that Microsoft shared their data with a select group of scientists before a recent conference, and those scientists weren't impressed.
They had doubts.
Yeah, lots of them.
About whether Microsoft has actually created these topological qubits.
Exactly. They think it's too early to say for sure.
So it's a real controversy.
It is, and it's playing out in public.
Which is kind of unusual for science.
It is, but that's how big a deal this is.
Everyone's watching.
They are, because if Microsoft is right, this could be revolutionary.
It could change the whole field of quantum computing.
It could, but if they're wrong...
It'll be a huge setback.
And a lot of wasted time and money.
So the stakes are high.
Very high.
But Microsoft is defending their work.
Of course they are.
They're saying they followed all the proper scientific procedures.
And they're emphasizing the peer review process.
Right, that's where other experts check your work.
Exactly. It's supposed to ensure that only high-quality research gets published.
So they're saying, trust us, we've done our due diligence.
That's basically it.
But the critics aren't buying it.
Not yet. They want to see more evidence.
More data, more transparency.
Exactly. They want to be convinced.
So this debate is going to continue for a while?
It probably will until there's more definitive proof one way or the other.
Okay, so we've got this big battle brewing over topological qubits.
Yeah, it's a real showdown.
But let's move on to something a bit more concrete.
All right.
Real-world applications of quantum computing.
We're finally starting to see some.
Yeah, it's not just theoretical anymore.
No, there are actual things we can do with these machines.
Like generating certified randomness.
That's a big one.
What is certified randomness?
It's basically a way to generate truly random numbers.
Okay, why is that so hard?
Because classical computers are deterministic.
Deterministic.
Yeah, it means they follow instructions.
So they can't just make stuff up?
Not really, no.
They can generate pseudo-random numbers.
Right, which look random.
But they're not really.
No, they're based on some kind of algorithm.
So if you know the algorithm, you can predict the numbers.
Exactly, and that's a problem for things like cryptography.
Where you need truly random numbers to generate keys.
Right, if someone can predict your random numbers, they can break your encryption.
So that's where quantum computers come in.
They can generate truly random numbers.
Because they're not deterministic.
Right, they're based on the laws of quantum mechanics.
Which are inherently probabilistic.
Exactly, there's always an element of chance involved.
So you can never be sure what outcome you'll get.
And that's what makes them good for generating random numbers.
And this is something that's actually been demonstrated.
Yes, a team of researchers published a paper in Nature just last month.
March 2025.
That's right, and they used a 56-qubit quantum computer from Quantinuum.
Quantinuum, okay.
Yeah, they're another big player in this field.
And they use this computer to generate certified random numbers.
Exactly, numbers that are mathematically proven to be random.
So there's no doubt about it.
No, they used classical supercomputers to verify the results.
So it's like a double check.
Right, they're using the best of both worlds.
Quantum to generate the numbers. Classical to verify them.
Exactly.
And they were able to generate a lot of random bits.
Over 71,000.
That's a lot.
It is, and they're all certified to be truly random.
So this is a big deal for cryptography.
It is. It means we can finally generate truly secure keys.
Keys that can't be predicted or broken.
Right. It's a huge step forward for cybersecurity.
And it has applications beyond cryptography, too.
Yeah, anywhere you need random numbers,
Like
scientific simulations, statistical sampling, even gambling.
So it's a pretty versatile tool.
It is, and it's just one example of how quantum computing is starting to make a real impact.
Okay, so certified randomness is one application.
What's the other one?
Quantum key distribution via satellite.
Ah, yes, that's another exciting development.
This one's all about secure communication.
Exactly. It's a way to share secret keys between two parties.
Keys that can't be intercepted.
Right. Even if someone is listening in on the channel.
How is that possible?
It's all thanks to the laws of quantum mechanics.
Again.
Yeah, those laws are really useful for this kind of stuff.
So how does it work?
Well, you basically send photons.
Photons, those are particles of light.
Right, and you encode the key information in the quantum state of those photons.
Okay.
And if anyone tries to intercept those photons, they'll inevitably disturb their state.
So you'll know if someone's been eavesdropping.
Exactly, and you can just discard those photons and start over.
That's pretty clever.
It is, and it's been demonstrated in the lab for a while now.
But now they're doing it from space.
That's right. They've launched a microsatellite.
A tiny satellite.
Yeah, much smaller than previous attempts.
And it's specifically designed for quantum key distribution.
Exactly. It has all the necessary equipment on board.
Lasers, detectors, all that stuff.
Yep, it's a miniaturized quantum communication system.
And they've already demonstrated it working.
Yes, they were able to generate a secret key between China and South Africa.
That's a long distance.
Over 12,900 kilometers.
So it really works.
It does, and they used it to encrypt and transmit images.
Securely.
Absolutely. No one could have intercepted the key.
So this is a big step towards a global quantum communication network.
It is a network where all communications are perfectly secure.
Unhackable.
That's the goal.
That would be amazing.
It would. It would change the world.
No more cyber attacks, no more data breaches.
It would be a whole new era of digital security.
So we've got certified randomness, quantum key distribution from space.
Those are just two examples
Of how quantum computing is becoming real.
And there are many more to come.
It's a really exciting time to be following this field.
It is. Things are changing so fast.
So let's wrap things up.
Right.
We've covered a lot of ground today.
We have.
We talked about Amazon's Ocelot chip,
Focused on reducing the cost of error correction,
Google's Willow chip,
demonstrating error reduction through scaling.
Microsoft's topological qubits.
Still a bit controversial, but potentially revolutionary.
And we talked about some real-world applications.
Certified randomness and satellite-based key distribution.
It's clear that quantum computing is no longer just a pipe dream,
It's becoming a reality.
and it's going to have a huge impact on our world.
Absolutely.
So as we leave you today,
I want you to think about the implications of all this.
what does it mean for you?
How will quantum computing change your life?
It's a big question,
But it's one worth thinking about.
because this technology is going to shape the future.
And it's up to all of us to decide how.